Now that we know how to multiply two matrices together, we should think a little bit about the properties of matrix multiplication before we go on and try to use this to solve equations. If you like, this is sort of investigating the rules you can use to hopefully make your life a little bit easier. Now, we said before that matrices are supposed to be something like a generalization of numbers, and that hopefully they act like numbers. We can add them, we can subtract them, we can multiply them together, and those are all things we can do with numbers as well as matrices. Some things work out in precisely the same way with matrix multiplication as it does with regular multiplication of numbers. We'll start with those properties first. Unfortunately, there are some differences that make multiplication of matrices a little more complicated than multiplication of plain numbers. We'll get to those at the end. So first, the things that work just as you'd hope they would. The first property that matrix multiplication has is something called distributivity. And all this means is that it interacts well with addition. So if A is an m by n matrix, and B and C are both n by p matrices, so they're the same size. In particular, we can add them together. So if we start by adding them together, and then we multiply them by the matrix A to get an m by p matrix, that's the same as if we did A times B plus A times C. This is something that you're used to from multiplication and addition of real numbers, and it works in precisely the same way for matrix multiplication. The second nice property is something called associativity. And associativity is about what happens when you try to multiply three matrices together all at the same time. So we could take A and B and multiply them together, assuming that works. And then we could take the finished product and multiply it by another matrix C. Or we could take B and C, multiply them together first, and then multiply that by A like this. And associativity just says that these two things are in fact equal. Or in other words, if you want to multiply a whole bunch of matrices together, it doesn't matter how you go about doing it, so long as the matrices are in the same order. You'll see on both sides I've got A, B, C, A, B, C. But it doesn't matter if I multiplied A and B first and then C, or B and C first and then A here on the left. So these are two of the properties that work precisely like the same properties for real numbers. We also have some special matrices, you recall. We have the identity matrix, and we also have the zero matrix. And these come in different sizes. And the zero matrix acts like 0, and the identity matrix acts like 1 for the purposes of multiplication. So here A is an m by n matrix. So we could say multiply it with an I sub n on the right-hand side, which is also an n by n matrix, and the result is an m by n matrix. And this is just the same as A. If we did it on the other side, we need to use I sub m. So this is an m by m matrix and an m by n. So the resulting thing is also m by n. And this is also A. So this is what happens when you multiply by the identity matrix. The identity matrix acts as 1 for the purposes of multiplication. And in fact, that's exactly the reason that we defined it in the first place. The zero matrix does the same thing. The zero matrix times A is always the zero matrix, and A times the zero matrix is always the zero matrix. As long as you pick a zero matrix that you can actually multiply by A on this side. So if A is m by n, then this 0 matrix needs to be, say, P by M, and then this matrix will be a P by N 0 matrix. So 0 acts like 0, identity acts like 1 for the purposes of multiplication. Those are the properties that work in precisely the same way for numbers on the one hand, matrices on the other. Now there's a kind of intermediate thing with the transpose, which is new. So this is a new rule that doesn't have any corresponding rule for real numbers. So the rule for the transpose is that if you multiply two matrices together and then take their transpose, this isn't the same as taking the transpose of A and multiplying it by the transpose of B. And that's because the transpose is like looking at your matrix through a mirror that somehow reverses its properties. So what we have to do is look at multiplication through the same reversing mirror. And what that means is that, in fact, we get that A times B transpose is the same as B transpose times A transpose. Now for general matrices A and B, if A is M by N and B is N by P, if you attempted to multiply A transpose times B transpose, you wouldn't even be able to do it. Now it is possible that the values of M, N, and P could match up so that A transpose times B transpose is a valid matrix, but it's still not in general going to be the same as A times B and then take the transpose. So this is our new rule, and now we're going to move on to the rules that are different from the rules for multiplying real numbers. And there are two of them. The first is that matrix multiplication is not what is called commutative. What this means is that A times B is not the same as B times A. Now, just as before with the transpose, if you can multiply A times B, there's nothing saying that you can even multiply B times A in the first place. The sizes might not match up. If they do match up, there's still nothing to say that A times B is the same size as B times A. But furthermore, even if they are the same size, there's still nothing to say they're actually the same matrix. It's pretty easy to come up with examples in all of these cases where either you can't multiply B times A, or you can multiply it, but you get a matrix of a different size, or you get a matrix of the same size, but it's still different. Not commutative. And finally, there's no cancellation law. So this concerns how you multiply things together to get 0. And it says that if A times B is equal to 0, then we do not know that A is 0 or B is 0. If you multiply two numbers together and the answer is 0, you know that one of the two numbers you started with had to have been 0. But in fact, you can find two matrices, neither of which is the 0 matrix, such that when you multiply them together, you do get 0. Now there's a further expression of the cancellation law, which is that if AB is equal to AC, then we do not know that B is equal to C. These are really basically the same kind of statement. In other words, you can't cancel things, so we can't cancel the A's like we could if these were real numbers.